Yes. Okay, very good. So when I ask you a question, you can just speak it out. You don't need to use the chat. I'm not all the time looking at the chat, so it could be that I'm missing if you write something. Okay, so a parameterized curve gamma. This is the Greek letter gamma. In R2, we start with R2. It's easier than R3, but the theory is completely the same. Yes. Okay, very good. It's a set. Yeah, so it's a set of points. So when I ask you a question, you can just speak it out. You don't need to use the chat. I'm not all the time. So the curve, sorry, I'm just fiddling with. It also has a motion, right? And that's somehow connected with the concept of curve, but technically it's just the set of points. So the path it took, just a collection of all points. Vector x of t, where vector x contains a first variable, x1 of t, and a second variable, x2 of t, and both of these are functions of t. So when you let t run between some starting point and some end point, a and b, you get a collection of points, and that collection is the curve. And the function x of t is called a parameterization of that curve. So gamma is the collection of points, and x is a specific function that takes you through all of these points, right? And then we call it the parameterization. Now, of course, there are many yeah, please mute yourself. One of the users are writing. Probably you get better sound effect if everybody is muted except me. So you can think of this as a runner along a trail. So every runner along the trail, they do the same path, right? But they can do it at different speeds and at different times. So there are so many different ways of parameterizing the same curve. Okay, so what is now the derivative? So we want to talk about things like, a curve in itself doesn't really have a derivative. It has a tangent. We're coming to that, but it doesn't have a derivative. But a runner along the trail, he has a derivative, which is velocity. So what would that be? And actually, instead of, well, I mean, you could take this as the definition, the derivative d dt, that's our notation for derivative of this parameterization here at the point t, is just the derivative of the first coordinate, comma, derivative of the second coordinate. So then that's another vector. By the way, do you all see me in a small window on your screen, or do you not see me at all?
We see you.
I see you as well.
Me too.
You see me in a small window, because then I think it's good, because I can maybe make just very crude pictures without swapping from the share screen, because that takes a lot of time, right? So if this is our curve, then a parameterization of the curve is like a function of t, so you follow this curve around. You can think of it as a runner along the trail. And then, okay, so the path itself, it has a tangent. Fair enough. But we're getting to the tangent later. Now, let me see, your chat is full. Okay, you're talking with each other. I always think you want to say something with me. All right, so if you want to talk to me, you have to speak out loud. Okay, so a runner at some point here, it will have a velocity, and that will of course be in the tangent of the curve, right? So let's talk about velocity first. How do we compute speed? Well, so if this here is x of t, and here I have x of t plus h, So h is a small time step forward. So here we have at 15 seconds and here we're at 16 seconds. If we want to compute average, well, the difference here where is at this time and that time is a vector, right? And now that vector, we can divide it with the time it took to travel from here to here. Yes? And okay, so that's some sort of average velocity over this 1 second from 15 to 16. That's the average velocity. Of course, then if we let h be smaller and smaller and smaller, we get an average velocity closer and closer to this point here, t. So it makes sense to define the velocity at t to just be the limit of that, right? And then this brings us back to the document here. So x prime of this, vector parameterization should be the limit of x t plus h minus x of t divided by h. But remember now, these are vector quantities. So this has a first coordinate and a second coordinate, right? So we write this out on this line here. We get the limit, here's the parenthesis for the vector. And in the first coordinate, you have x1, t plus h minus x1 of t divided by h. Second coordinate, you get the same, right? And then you see that, okay, so limits of a vector. You have something that depends, in this case, on h. You have a first coordinate and a second coordinate. The limit of that, we define it, you just take the limit of what is going on in the first coordinate and what's going on in the second coordinate. So this limit here, you can move it inside just by definition of what we mean by limits in several variables. Right, so once you move the limit inside, you see that, oops, this is exactly the definition I know for derivative, right? And x1 is a one variable function. So now we're back in calculus 1. So you do that and you get x1 prime and x2 prime as the two coordinates. So now we have defined a new vector quantity like this, and that we call the velocity or the derivative simply of the parameterization. So one small point about visualization. So where did the pen go? Well, anyways, so I do this, I divide by h. Yeah, so then maybe up on division by h, I get this vector. And then I take another point here, I compute the tangent, I divide by h, and I get another vector, maybe this one. Yeah, so you see these ones get shorter and shorter, but after division by h, you get some length which is more or less converging to something. So at the limiting point, you get a vector here that is completely tangent to your curve, and that's what we call the derivative. Oh, and about visualization. So there's always some origo somewhere when we think of this. We're working with a coordinate system, so there's some point which we call 0. By the way, of course, 0 actually means 0, 0 with a parenthesis, but we are usually lazy and we just write 0. So this, yeah. Anyway, so when I paint a vector here, this is just for visualization purpose. You have to understand that what I've done, actually this red guy here, he lives down here because all vectors start at 0. The vector is just two coordinates. So you think of it as an arrow from 0 to that point, right? So the derivative is this vector down here. The reason why I paint it up here is, you see, I just translate, I take the origin and put it at the point where I am on the curve, which is very natural to do, right? Because this is where we are, so it makes visual sense to put the arrow here. But just to point that out, that So this is visualization. Technically or mathematically, the arrow sits down here. It's a vector. Well, it's a coordinate pair if you want. It's two values, but if you visualize it, technically it should be a vector from the origo to that coordinate pair. Okay. Right, so naturally, just by how we derived it, this becomes velocity. And if we want speed, that would be the length of the velocity vector, right? So velocity has a direction, speed does not, it's just a value. You know, it's when you drive your car, it doesn't tell you if you're going north, south, or east, it just tells you you're going 90 kilometers per hour. So how do you get that? Well, you take your velocity vector and you use Pythagoras theorem to compute the length. So that's what we have here. And yesterday we introduced also norms of vectors. So we know that one way we can write this mathematically is using this norm notation. Sorry. So we put two dashed lines here and two dashed lines there, and that means norm, which in Rn just means use Pythagoras theorem or formula. So we square the coordinates and then take a square root. Now, of course, this can be iterated. So if you now look at the velocity at two different points, which are very near, divide by the time difference and take a limit there, then we get acceleration, yeah? That's the change in velocity. So again, that's a vector quantity just obtained by differentiating twice. So to look at an example, we have the unit circle. And again, a path, a curve is a set of points. So one way to say, here's the unit circle, you just say, look at the points that fulfill this equation. So gamma colon mean gamma equals, this is a bit sloppily written actually. I mean, you shouldn't be using this bird wing notation. So gamma equals bird wing notation, x1, x2, such that equation is satisfied. But of course that gets lengthy to write. So like shorthand notation is like gamma colon, and then you just write the equation you want to satisfy. So now here we don't have a parameterization, right? It's just a collection of points, but that's where I started. A path is a collection of points that can be parameterized. It's not any collection of points. You know, the unit ball with everything inside is not a path. So, but the unit circle, we, you know, just by looking at it, but we know it can be parameterized, meaning it can be expressed as a function of one variable. And what's the easiest way to do that is to use cosine and sine, yeah? But there are different ways of doing this. So you can go, with cosine and sine, you go around the circle at a constant speed, yes? But that constant speed can be either fast or slow. So to make the example a bit more interesting, we introduce here an omega. It looks like a W, but it's almost the same. But right, so cosine omega times t, sinus omega times t. So t is the variable here, and omega is just some fixed value, and that's called the angular velocity. So you go around here. So the amount of t's you need to make a complete revolution is t's between 0 and 2 pi divided by omega. Because then, yeah, for the end point over here, you reach 2 pi here. Okay, and then we can compute the derivative. What happens is cosine becomes a minus sinus, sinus becomes a cosine, and this omega pops out as an inner derivative, right? So we get omega times this. And if you look at this, I mean, the scalar product of this guy and that guy is clearly 0. because you have sinus here, we have cosine there, you have sinus here, you have cosine there, and there's a minus on one of them and not on the other. So these two just cancel out. So what we see here is that all right, so the point is a vector from 0 to here, yeah? The derivative is perpendicular, which is kind of obvious, right? Just by looking at the geometry of a circle. And then again, if you take the acceleration, you know that when you go around the circle, you're always accelerating towards the center, and that we see here, you get another omega pops out, and we get back the original vector cosine times comma sine, but now with a minus omega square, so it points in the inside direction, whereas the actual point is in the outside direction. So yeah, and omega pops out, so that justifies, you know, angular velocity. If we compute here the speed at this at any point, we're just going to get omega, right? Why? Because this is the trigonometric identity. I do square root of omega, was it minus sinus omega t in the square plus omega cosine omega t squared and n square root. So here I get an omega square, here I get an omega square. So this I can pull out and the square disappears when I do the square root. And I'm left with the square root of sinus something squared plus cosine something squared. And as long as something and something is the same something, that's the trigonometric identity telling you that that is equal to 1. So the only thing which is left is omega. So that's the velocity then. Okay, here's let's look at some complications that can arise. So another parameterization, which looks very nice, of another curve. So here we don't start with an equation. Here we start with just, okay, here's a parameterization. It gives some set of points, and then you look at it as, okay, you say t3 and t square. Well, how can that look? And you start to think about it, and it's hard to visualize, you know? You need some feeling for how T3 and T2 looks like, and then how you put together them. So what happened now? Okay, here we are. So one way of doing this is now we go backwards. We didn't have an equation like in the previous example, but we can try to make one. Yeah? So how can I make a relationship that's always true between the first and the second coordinate here? Well, I say, if I raise this one to the power 2 and this one to the power of 3, I get t to the power of 6 in both cases. And then actually, you know, then I get the relationship x1 square equals to x2 to the power of 3. Now that I can do some algebra with, right? So now I can free x2 by taking a cubic root on both sides, and then I get x2 equals x1 to the power of 2/3. So this is something we know how to plot, right? So anytime you have an exponent here less than 1, it looks a bit like the square root. The square root is the one we know the best, but here we get, okay, 0.60. It doesn't look very different. And then here's a bit of a technicality you have to think about. So usually x to the power of something only exists for non-integers if x is positive. There's a bit of a peculiarity here that if this is a rational number up here with an odd number in the denominator, then you can actually extend it to the negative axis. Okay? It's not something to think too much about, but up here you clearly see that if t has negative numbers, you get a negative coordinate in the first and a positive coordinate in the second. So we clearly want numbers over here as well. So we extend it like this, right? So it clearly must be symmetrical, right? Whatever happens at minus t is the same at a positive t. If you flip the sign, the only thing that happens is that the x-axis coordinate flips between minus and plus. So we need a symmetry here. But the interesting thing here is at the origin, we get this like square root look of the curve, right? Meaning that we have some sort of singularity here, right? So I was just telling you we can always compute the derivative or the velocity, but here we cannot. Yeah, there is no vector I can put tangent here. So this is something we have to be careful about or cautious about. And what? Okay, so points like this are called cusps. And the problem, what went wrong here is that you see if you differentiate, if you look at the velocity, it's actually 0. So this is like some object comes here and slows down and just comes to a stop and then takes off again. And clearly then you can have a sudden change in direction like 90 degree or whatever degree, right? So this is an exception, and we don't like that because we want to work with curves which have tangents and so on. So we're going to add a bit of terminology here and say that a curve is smooth if it has a parameterization which is differentiable functions. Of course, not even that is a necessity. So yeah, here we're borderlining many peculiar facts. So there's a thing like, for example, you know, as a curve, you think of it as taking a pen and just start painting, right? And if you imagine that in your head, you say, all right, that's going to be something, you know, I can follow with my eye. And no matter for how long I paint, you know, if you take a pen has like a finite width. So if you do long enough, you can actually make an area completely black. But the graph of a function is infinitely thin. So intuitively, you would say that, okay, this will be a curve that, you know, it can never fill up an entire area. But this is one example of many where mathematics intuition leads you to a false conclusion. So there are things like a space filling curve. So basically you start painting and at some point you have passed all points in a square. Actually, you can fill the entire plane if you just do it long enough. All right, but so those examples are arising if you remove things like, if you look at very functions which are not well behaved. So we usually in mathematics try to restrict attention to functions that are well behaved. This is more pronounced in physics. In physics, they usually write, you know, let f be a well-behaved function, and that well-behaved never has a proper definition. It basically means a function such that my conclusion here is correct, which sometimes is a void space. But all right. So in mathematics, then. So usually you look for functions that has a certain amount of derivatives, and this we call smooth. So again, this course is not very technical, so we don't really go into it. But a parameterization will be called just smooth if it has two derivatives, each coordinate has a derivative, and those are continuous functions. So a more appropriate or correct terminology is down here in the remark. It would be called C1 smooth. So C stands for continuous, 1 stands for one continuous derivative. So then you can have C2 smooth, C3 smooth, then you have 3 derivatives which are all continuous. The third one is continuous as well. And then at the end of it you have C infinity, which means all derivatives are continuous to any given order. Okay, right. So that's smooth. That's just requiring derivatives to exist. And to avoid cusps, we also need to avoid points where the derivative is 0. So the curve being smooth is these two concepts. that the functions are smooth and that there are no cusps, no point where the derivative is 0. Note that one coordinate of the derivative can be 0. That's not a problem, you know. Otherwise, we would not allow, for example, a rocket going straight up because it has no velocity in the x direction. As long as there's a velocity in some direction, you're good to go. Okay. Right. So a runner along a trail can have completely different velocities, but the trail itself at each point has a direction, right? A tangent, which is completely independent of the runner. And to get to that, if we have now one parameterization, so when you do the derivative, you get a vector in the tangent direction of the trail, but it has different length depending on who's the runner. You know, some people run fast, others run less fast. So if we divide with the speed, we get rid of that, we get a unit length vector, and that's what we're going to call the tangent. So the tangent is independent of the parameterization, right? At least except for maybe direction. You can run forward or backwards along a trail, right? So t of x, actually this t here, if you have a parameterization is t of x of t, then you just do the derivative and divide with the length. But then you realize that this is actually independent of t, so you just introduce t of x. That's the tangent vector. Okay, so now that was a bit of definitions. Now we got through them. Here's another definition. Piecewise smooth. Well, so why do we speak about curves? Well, of course, it's interesting in itself to be able to describe trajectories of airplanes and missiles and what you want to use your mathematics for. But also they appear as boundaries of other objects. So if you do some mathematics inside a square, then the boundary of a square is a curve, but the boundary of the square has sharp corners, right? So if we don't allow, you know, we want to have a definition or work with a mathematical framework where we avoid things like the space filling curve, because then, you know, that's not it doesn't correspond with our intuition of what is a curve. But on the other hand, we don't want to make it so strict that we exclude natural objects like the boundary of a silly square, right? So then you have to do some trade-offs here. So at the end of the day, the curves that will be interesting in are the piecewise smooth ones, and that's simply a curve which is made up of a finite collection of smooth curves which meet at the endpoints. Yeah. So here you have a smooth curve, full stop. Then from that point, picks up another curve, full stop, and then like that. So if you have the union of all these curves, as long as they meet at the endpoints like that, then you call that a piecewise smooth curve. So this boundary of a square would be made up of 4 smooth curves, which is each of the 4 sides. Now, one thing we haven't discussed is direction. This so you can go forward and backwards along a curve. And we also haven't discussed, okay, we said several times that, okay, there are different, you know, a runner can run along a trail at different speeds, so there are different parameterizations, but how do you go from one parameterization to another? So let me do some painting here again. So here's the trail, yeah, and here's a runner, he runs. So this is a function x of t. But then comes another runner and starts to run a bit later. And that trajectory is y of t. But I mean, this t variable starts at this one started at a later point even. So we don't need to call it t. So her clock can be called s, yeah? And this guy's clock can be called then just t. So they're passing the same points, but they're doing so at different times. Now, if I know how, if I have x of t, and I want to go, I want to know y as a function of s, right? One way of doing that, instead of like just measuring this purple runner, I could say, okay, I know already x of t, so I know the path x took. If I then know the function that translates, okay, at what time t, so here we're at the point s, yeah, in the time of the purple runner. What time t corresponds to that point when x passed that very point, right? So if I have So if I have a function t as a function of s, such that, at point s in time, t of s is the time when the first runner passed that, then I can go between these two parameterization. Okay, so this, if you think of it like that, it's very natural. So this t of s is now just moving the clock function, right? But here are some complications. So note now, and this is common in math, t here is now, it suddenly became a function of s. So we have collision of notation, and that is making life so much simpler than if I would call this some other letter, G or so, right? But you have to keep it separate in your head. Here, t is just a dummy variable, and over here, t is a function of s, right? So what is this t of s? So if the yellow guy started running at A and finished at time point B, and then this purple guy started running at A tiddle and finished at B tiddle, yeah, then what I have here is on the x-axis, or rather the s-axis, I start at A tiddle, I finish at B tiddle, and this function t of s is a one-to-one function between the interval A tiddle, B tiddle to the interval A to B, yeah? And it has to be increasing, because always, if y moves forward, he also moves forward, so time only moves in one direction. So this is something we know from analysis 1. Increasing continuous functions, they were also called bijections, and there were some theorems about, you have this intermediate value theorem and so on, so we could characterize that each bijection from one interval to another interval is always either an increasing function or a decreasing function. Now, because, okay, so first observation is, if I have one parameterization x of t, I can clearly go to any other parameterization by doing a change of variable like this, right? So this can also be used, okay, if we don't have the second runner, I just have x of t, I can invent the function t of s, plug that into it, and now I get a new parameterization. So this is easy. Once you have one parameterization of your curve, you can just make up other ones by doing bijective, by throwing in bijections like this, one variable. In fact, it can be proven, we're not going to do it, but it's kind of intuitive that all different parameterizations arise in this way. But okay, now we come to this, that you can actually run this thing backwards. Yeah, and that is something else. So what if I do a change of variable or a bijection, but like this?
Excuse me, I can't seem to be able to see the button.
When I'm at a tiddles, when I'm at the starting point for the s-axis, I actually put myself at b, which is the end point, right? And then I go down here in time, meaning I follow this curve backwards, right? And that is, in our mind, something quite different.
Excuse me, I can't see the bottom of the blackboard.
Wait, I'm just checking the chat. Are you telling me to speak louder, or what's going on? Is there a hearing problem? Oh. Sorry about that. So on the s-axis, there's just a tiddle and b tiddle written, and then on the t-axis, we have a and b. Right, so okay. Well, so yeah, I'll just move on. If somebody wants me something, either you write it here or you try to talk. But let me check that my sound is actually on. No, it wasn't. All right, so that makes sense. This is a great way to avoid any sort of criticism or whatever. You just tell people to speak out loud, and then you put the volume to 0.
Can you hear us now?
Now I can hear you. Yeah, I was like, why are these guys so silent? Very timid crowd. Yeah. Okay, shall I just move ahead, or should we chat about something?
You can move on.
I move on. No. All right, so this function here, okay, now he calls it phi. He has a bit of a different notation here. He calls tau. I introduced new variable s. He has tau, and phi of tau is the bijection. He has alpha and beta. I wrote a tiddle, b tiddle. But anyway, it's the same thing, right? So as long as phi goes up, or this function here, t of s goes up, we're just following the path the same way around. So this is called a reparameterization, but it still gives the same curve. But if we do it backwards, we get a new mathematical object, which we call actually, so if this is gamma, then this gamma followed backwards would be minus gamma. We just call it that. So the minus, this is just a symbol, minus gamma. It means the parameter is gamma, but you do it in the reverse order. But this somehow collides actually with my first definition, as a curve is just a collection of points. But then I say, well, we have to refine that because there are these space filling curves. So it's not really a collection of points. It's a collection of points that has a parametrization. Okay, so then it's a bit more complicated. Yeah, it's not only a collection of points. And now I'm telling you that, yeah, but okay, so the parametrization is not that important. But if you flip the direction of it, then I'm going to call it a new object. So a curve is a collection of points that can be parameterized, and as long as the parameterization start and end in the same point, if you have different parameterization, we think of it as the same object. And if the parameterization of one curve and another curve, if it's the same collection, but the direction is different, then we don't think of it as the same object. We think of one as being negative, the other. So these are curves with orientation, if you want. And okay, then here comes more terminology. So of course, then we can have the problem that a curve can intersect itself, which usually we want to avoid, probably because depending on the situation, whether we want that or not. But usually when we work with boundaries of domains and so on, this never happens. So that will be called a self-intersection. And a curve is called simple if it doesn't have any self-intersection points. And it's called closed if it starts and ends at the same point. Which is usually we want to study close, simple curves because those are boundaries of other domains. So there's even a own name for that. I mean, it's not a long thing to say simple closed curve, but it's called a Jordan curve as well. And that's, well, actually, if you look at the technicalities, Jordan curve, it has a bit more to it. So it needs to be, here we work with smooth curves. The Jordan curve needs to be rectifiable, which is somehow taking the lowest amount of smoothness you can have. But it doesn't matter. This is just a curious side remark. So, okay, there is this concept of Jordan curve, which basically just is mathematically made in the simplest way to describe what we think of as a closed loop. Yeah. So, you know, these puzzles, find the way out, you know, that somebody had painted a lot and you have to start in the middle and then you like follow and see if you can. But so clearly such a path can become very complicated, but still we kind of understand that no matter if I start painting and the zoom, I go in and out, as long as I don't cross my painting, right? And as long as I stop where I started, I have now made something that divided space into an outside and an inside. A super simple statement, you know, after at least, you know, 5 minutes thinking about it and a bit of human intuition, you will say that, yeah, that has to be true. It took them like, I don't know how long they were working on it, but this was a big open problem for a long time in the 1800s and solved early 1900 or late 1800, I'm not sure, by this guy Jordan. So the reason why it's called a Jordan curve is more like to honor his name for actually finding a solution. And the solution is not, I mean, it's very difficult mathematics. So if you ever take the course topology, which, yeah, it's not in the course topology, but if you do the course topology, you will learn the tools to understand that proof. So, yeah. All right, here's a bit of, how do you call this? You know, when you go, these roller belts that take you just from a point A to B, and it's very boring to stand on them. You know, you're at the airport and you have to go far, you just stand there. And you can also, you can try to walk, but there's always a couple who stands in parallel and then you have to, you know, kind of, sorry, and try to get by and they frown on you. So at the end you give up. You just stand there like a vegetable. Conveyor belt, yeah. All right, so this is a conveyor belt section of the class. So once we introduce a new something, we have to introduce also computational rules that goes along with it. So that's here it's very direct. So yeah, okay. First of all, we can do this in 3 variables. Nothing changes. So the velocity will be, in 3 variables. You have 3 functions making up the 3 coordinates. You can differentiate each one of them with your Analysys 1 tools. And if you make the triple of those 3 derivatives, then you have the velocity of your 3-dimensional curve. And then we can add curves, of course. So yeah, you just add, well, you can also add, no, I take that back. You cannot really add curves because you need to know which point on one curve to add to the corresponding point on the other curve. But if you have 2 parameterizations of 2 different curves that run on the same t-axis, time axis, then you can add that. So you can add a function, a several variable function of one variable to another one. And then you differentiate that. And this is just, since all of this boils down to doing one variable calculus on each coordinate individually, there's nothing new to prove here, right? So whatever formula you remember from calculus 1 will apply here as well by just direct. So the derivative of one curve plus another, or parameterization plus another, is the same as the derivative of one and then plus the derivative of the other. If we have a scalar function lambda of t, what does that even mean? It means that you put lambda in front of x1, lambda in front of x2, and now if lambda, right, is a function, so it depends on t, what we end up having here is a product, right? In each coordinate you have lambda times x1, second coordinate lambda times x2, and what happens when you differentiate products? You have the product rule, right? So first you need to differentiate lambda, you don't differentiate the x guy, and then you leave lambda untouched and you differentiate the x guy. So we can sum up those two. Lambda, the derivative of lambda is the same for all coordinates. So here we just get lambda prime times x. And for the second coordinate, then we didn't touch lambda, but we differentiated x. So yeah, the derivative of lambda times x is the derivative of lambda times x, plus the velocity times lambda. So you can cook up funny rules like this, and you can also differentiate scalar products. Just the same here, just write it out, and then you see from your calculus 1 what this expression is going to be, right? So this is not something to really memorize, I would say. But maybe worth pointing out. So it's, no, it was pointed out. Here it is. Well, right, just small example. Cosine t, sinus of t, we go around, yeah? Circle in the plane. But now if on the third coordinate you add a t, it means that linearly, or linearly means with constant speed, we go up in the c coordinate, right? At the same time we rotate in the x and y plane, so what we're going to do is a spiral like this. Okay, so this is called a helix, like the attraction on Liseberg, which is now closed. So we can differentiate that one, and Okay, so now he just gives an example here of the computational rule. So now if we multiply that with a t again, now we get a new thing that actually, so it starts like this, it goes very slowly up, and then it goes faster and faster and faster. So this is like some rocket spinning out of control. So if we want to differentiate that, we can use this rule that we first differentiate t times x of t, and then we don't differentiate t, but we differentiate that guy, the curve. So then here's an application of the second computational rule on the previous theory, and then we can plug it in and just compute it. So it's not so interesting what the final expression is here, but just to see. Of course, we could just differentiate, write out what this is. You know, if you have t times cosine of t, t times sine of t, and a t square, it's not very hard to differentiate that either. By the way, there must be something wrong. There's something wrong with this example, because here it says t plus 1, right? But the last coordinate of t times x of t, here you have a t square, right? So we know that's 2t. And why is that? Aha, look here. Here's a t, and there's a t times this. But he forgot to multiply this in here. And yeah, there's a computational mistake here. The lecture notes we follow, as you kind of hear, it's not made by me, but I've used them for several years. They are excellent, I think. So it's much better than what I would be able to produce myself. So it's for the best of all. But there are some, you know, occasionally find some error here and there. That's always. So here's a good example of why you should write out intermediate steps in the exam. Because if I see this in the exam, I would say that I just made a silly error and I won't even bother to take a point. But if I just see this is the answer, then I say, well, the answer is wrong. Take many points. Okay. Jesus, I talk too much. I would recommend, we started late, so somehow we shouldn't have a break, but I would like to go and get some coffee. How about we take like a half break? So it's, I don't see my clock, but my clock here on the wall is 3 minutes to half. So I start at 9:35 according to this watch, which is in 8 minutes. So you can tune that to your personal watch, and see you soon. drinking this coffee it's a bit like, you know, when you're a kid and you go to the swimming hole and you have this jumping tower, like jumping from 10, it always seems like a good idea when you stand there, you look up, it's like, yeah, I can do that. It looks funny. And then you go up there and you go, what the fuck? You realize this was a completely bad idea. It's completely the same with this coffee. I mean, after 1 hour of talking, you want some, but I don't know how you can destroy a product so completely. I mean, the coffee beans that goes in there are actually nice. There's nothing wrong with that. It's just something in the processing. But no, I don't know if you're coffee snobs or not. I'm not a big coffee snobs, but they have this Suega. I think it's a decent. I use it at home at least, and it doesn't taste like this. Well, all right, so my clock is what I said it would be when I start, so now I start. If we have a parameterized curve, we could be interested in its length. Yes. If you want to get fast to how to solve the exercises, I'll change a bit of order here and just tell you the two relevant formulas. So, if you want to know the length, so you have a parameterization from A to B on some time axis, right? This is the function x of t that starts here. Here is x of A, and here is x of B when you're done, right? So you go through here. Now, what's the length? Well, clearly the length is the area under the speed, right? The integral of speed. So what was speed? It was the norm of the derivative of our parameterization. So this is now a one variable function between A and B, right? Something like this. That's the amount of meters per second that the runner has at each point. Now, if you integrate that, this is just analysis 1. If you integrate speed, you get length, right? So the length has to be the integral from A to B of the speed. And that's, yeah, that's a very easy formula to remember as well. Much easier than the one I'm going to write now, the second formula you need. Sorry for the bad planning of the disposition of Blackboard, but the most common type of curves we actually look at are graphs.
Sorry to interrupt, but is there anything you can do to fix the zooming or the focus of the camera?
Oh, Jesus. Yes, of course. You should not be sorry to interrupt. You should interrupt anytime there is a problem, especially with the focus of the camera. No, I think I have to stop my share to do that. And then exit full screen. This is a bit, is this the guy? No, that's the wrong one. I'm not allowed to close the window. Okay, so now I am, but how is the, is it good now? Is it?
It is good now.
Okay. I don't
But
know why
you-
this can't focus. It's completely annoying. It always goes on by itself and it's complicated to find where to turn it off. All right, now we go back. Where we were, share screen. And here I was. And then we do a. Okay, so I've always talked of curves as something, now it has a first coordinate and a second coordinate, and that's the natural way of thinking about them. But if you think of a one variable function, we always paint them as a, maybe this light is better also. We paint them like this, right? This is the graph of a function. And if you look at it, it's a curve, yeah? But now what we're dealing with here is a function f from an interval a to b with values on the real axis. So this is, you know, a curve, you need two functions. But here you just have one variable function. But still the object looks the same. So what's the bridge here between these two worlds? Well, to think of a graph as a parameterized curve, you just need to realize that each point here, the x coordinate is always t, and the y coordinate is always f of t. And now look at it, it is actually a pair, where the first coordinate, the x1 function, so to speak, x1 of t is just t itself, is the identity function. And x2 of t is equal to the function f, right? So to think of a graph as a parameterized curve, you just set x1 of t to be equal to t and x2 of t to be equal to f of t. Right. And then, okay, then if you want to know, okay, what's the length of this graph? So I write it here, sorry for the bad disposition of the blackboard. Well, I still need to use this formula, right? So this is the length of the graph is the integral from a to b square root. And then I have to do x1 derivative. But that's just one, right? If I differentiate t as a function of t, I get one. And when I differentiate x2, I get f prime, right? So here I get 1 squared plus f prime of t squared, the t, and of course 1 squared, that's just 1. So here you have the second function formula that you have to memorize, or not memorize, but know to solve the exercises. But here is what I want to underline about how to learn mathematics. You should definitely not memorize this one. This one, I mean, if you understand what I said, that if you integrate speed, then of course you get length. Then you don't even have to memorize anything, because then this is just a completely natural statement. Like, you know, the sky is blue, except if you live in Skåne, because then it's always gray and it's annoying. But, right, but this one is natural. This one is not natural. So if you want to remember this one, then you have to make an effort, but your head will soon be full of similar formulas which are not natural. So if instead you remember how you got here from this one, then that actually requires less memory storage, right? At the cost of a bit more processing. Because, yeah, so this derivation, set x1 to t equals to t, x2 of t equals to f, is not hard at all. And then you plug it into this formula, you get this one out. And then that's how you can, instead of memorizing it, you just remember how to derive it from something natural. This is my recommendation.
A question.
Yes.
How do we know that all the integral is equal for all parameterizations?
Right. So this is okay. So far, what I've been doing is this like hand waving, non-rigorous mathematics. Yeah. So I said, basically, I said this is natural to say that the length should be this. So let's just agree on that. But that's not how you do mathematics. And your question is very good. It points, its finger to what can go wrong if you sloppily do math this way. Because yeah, I've introduced curves as something which is independent of the parameterization, apart from the length. So sorry, apart from the direction. But in my definition of length, I use a particular parameterization. And then, of course, for this to make sense, I need to prove that this is independent of the parameterization I use. But there is an even better approach. So this is true, it's possible to do, but there's a better approach. And the better approach is actually to make a definition which is independent of the path. And then prove that for any parameterization, you reach this expression. Because then that goes for free, right? Because if your definition is independent of path, and then you prove that your definition is that integral, it's the same integral for all paths. So then you get that for free. So that is the more technical part of what we have left here. So I said I do it backwards so that you get the formulas you need immediately. But let's go back to page 9 here and introduce arc length, which is what it sounds, the length of an arc. But we're not going to do it by an integral like this, but we're going to do it in a more basic fashion. Actually, I think from now on, I will just be talking. So what I will do now is I will introduce what's written on page 9 and 10 to make this intuitive. Then the formulas here, this theorem 2, which says that the length is actually given by the formula I already gave you. And then on page 14, you have the other formula I gave you. And in the end here, beyond that, he does some yada yada with this ds, which is a bit of a fishy concept. I want to explain that in more detail next time, because next time is not, it's a more relaxed lecture, and it continues here. We're going to talk about arc length parameterization, which is so now we're talking about arc length, and arc length parameterization is a different thing, right? So if you could please wait outside until it's 10 o'clock, I would appreciate it. Right, so when we do arc length parameterization, I will tell you about what is the ds. So right now you can think of it as some sort of a bit just, it's a bit, yeah, just hold on until Friday about this ds. Don't waste your energy thinking about it. Okay, so if this is my curve gamma, and I don't have a parameterization, I want to give a mathematical definition of the length of gamma. How can I do? Well, what I can do is I can come up with approximations of the length. So the only thing I really can measure distance is between 2 points, right? So here is the point, let's call it x1. Not to be confused now with the first coordinate of our parameterization. This is just a point x1, so there's a bar on top of it. It's a vector, yeah? And then I take another point on my curve, call it x2. And then I can measure the length here. That would be x2 minus x1 in north. Yeah, and this is clearly an approximation here. I mean, this curve bends a bit, so the actual length of this segment is going to be a bit longer. Of course, I could add a point here in the middle and get a better approximation. Yeah, but we're not going to do this. This is our first length, and then from x2, I take a different point here, x3, and I do a straight line here. And now the length of that guy is going to be x3 minus x2, right? And then we do this again and again and again and again and again. So at the end of it, we come to some point here, xn, where n is the amount of cuts we have made, right? Modulo plus minus 1, something like that. So with 1, yeah, so if n is the amount of cuts, then here is n plus 1, because you know, there's this thing like if you have columns in these Greek buildings, or like a Capitol in the US, you have columns. So how many spaces are there? Well, there's always one more column than there are spaces, right? So that's completely not the point. The point here is that if I want an approximation of the length, I can sum up these guys. So I do x2 minus x1 plus x3 minus x2 plus dot, dot, dot. Now this notation becomes very tedious to do this plus, 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 dot, 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 very amateur style. So we have to find a mathematical way of writing sums. So we have this symbol, it's the summation symbol. It looks a bit like the Greek letter sigma, but it's not, it's just a summation symbol. And now here I write j equals to 1 up to n minus 1. And then here I write xj plus 1 minus xj. So how is this supposed to be read? I guess you have seen them before, but just to do a bit of recap. When j equals 1, you insert that here, you get x2 minus x1. Well, that's the first guy here, right? When j equals 2, you get x3 minus x2. That's the second guy here. And so if you do that for all j's between j1 and n minus 1, then the last one is xn minus xn minus 1. Oh, sorry, I said I should stop the sharing, so maybe now it's okay. So this is just a way of mathematically writing, just sum up all these lengths, okay? So for each small section here, this length is actually shorter, right? Because the straight path between 2 points is always the shortest road. So this is an approximation, and it's an approximation from below. The actual length is longer, and the more cuts you put here, the closer you will get to what is intuitively the length. So let's take and define the length L of gamma is defined as, and now we come to this concept, supremum. You should have encountered in analysis 1. So what is a supremum? You know, if you have a collection of points on an axis, the supremum, you know, we have this idea of an upper bound. Okay, upper bound is just any number which is higher than the collection of points. And then this lowest upper bound, that's you take the infimum, so you go as far down as possible as the least upper bound is what it is called. So that's the same as the supremum of this set. So yeah. Okay, so you're supposed to know what that is. I'm sorry, but that wasn't the most pedagogical explanation. But anyways, so we have a set. The set will be all sums of this type. So here's a set. What we get here is a number. For every time I cut up my curve like this into finitely many points, I can compute this number. A selection of points that can be, we don't know how many, I mean, there can be different amount every time. It's going to be called a partition, right? So a partition is just take a bunch of points on the curve in some order that you go along the curve. And then for each such partition, you can compute this number. So now we have an uncountable amount of numbers here. This is a set. Yeah? So it's some values on an axis, and then somehow intuitively the biggest such value, which might not exist. That's why otherwise we would just say, okay, the maximum of this is the length of the curve. But the maximum, if it doesn't exist, we have to call it supremum instead. So this is the least upper bound for this set. Okay? Now that makes sense. That's a completely intuitive definition of the length. What we need to do now is to go from this definition to the formula. And the details are in the lecture notes. So I'll just briefly give you the idea there. So what do we have? You see what I'm writing now, yeah? So we have this sum. So one of these parameterization, it looks like this. Sorry. So one of these approximations of the length, it looks like this. And let's see if we can work with this expression, because clearly this is not a nice object to work with, right? You need a computer to compute this finer and finer and finer, because you need at some point to get the actual length, you need to let the amount of points go to infinity. So what do we have here? We have a sum square root okay, so instead of xj plus 1, okay, let's do it like this. So I can write this is the parameterization x evaluated at t, j plus 1, right? Minus x at t, j. So instead of thinking of this as a collection of points on the curve, I think that down here I have my time axis from A to B, and I just chop that one up. Yeah, so T2, T3, T1 being A, and so on up to Tn, which will then be equal to b. So that's equivalent to what's going on up here, right? So for each cut in my time axis, I get a point on my graph. Okay, now I have this sum. And what is this? This is the sum. K goes from 1 to n, square root x tj plus 1 minus x tj x1, so first coordinate, square, plus, and then the same thing with the second coordinate, right? So now x1 and x2 are the first and second coordinate, not the same as the x1 and x2 here, a bit of collision of notation, hope you can live with that. Okay, and then the square root closes here. But, oh, we need a square here as well. So still this doesn't look like much, but differences are connected with derivatives, right? So if I here do a division by tj plus 1 minus tj, then let me put it in front. Now I divided with that inside the square, and then there's the square root. So if I want to, revoke that operation, I have to also multiply in front here with tj plus 1 minus tj. And now this starts to look like, these are approximations of the derivative of x1 at the point tj, right? This is an approximation of the derivative of x2 at the point tj. So this is approximately equal to the sum. I'm going to flip the order of the square root and that guy. So here I have approximately equal to square root t x1 prime evaluated at tj plus x2 prime evaluated at tj with a square, and here you have tj plus 1 minus tj. And if you know or remember your analysis 1, this is a Riemann sum. Yeah, we can write this a bit shorter, like sum j goes from 1 to n, x prime, now with a bar on it, evaluated at tj. So because here we just have the norm of the derivative of x as a vector. And then times tj plus 1 minus tj. And if you forgot what is a Riemann sum or a Riemann approximation of the integral, I advise you to refresh your memory, because this should look familiar to you. This is a Riemann sum for how you integrate the function x prime in norm, right? So you take values of x, now I'm out of Blackboard space. So you take if you look at the function x prime of t, this is just a one variable function, right? If you want to do an integral of that or a Riemann sum for that, you do different tj's, and here's your function, here's your chopping of tj's, and the function value times tj plus 1 minus tj is just the area under one of these guys, right? So what we have done here is something that looks like this. And that's a Riemann sum approximation of the integral. So here we have a Riemann sum approximation of precisely this formula I gave you up there. Where is it? What we have here is a Riemann-Sum approximation of this formula here. So now it's all kosher. Of course, we have jump details here, but we define the length to be this supremum. For each sum that goes in the supremum, we can show that this is arbitrarily close, or we can control the error between this value and the corresponding value for this integral, and with a bit of mathematical epsilon delta drilling, you can actually prove that this supremum here, which is independent of parametrization, actually equals this integral. And then we have defined the length, or we have validated this formula, and then you get for free that it's the same formula independent of parameterization. Okay, I went a bit over time, but also I started late. I'm sorry about that. Flat tires. I don't remember. I think it was the 90s last time I had a flat tire. The coffee I get at the 4th floor. And actually, I think I blame myself a bit because I was part of some committee 15 years ago about, you know, updates to the coffee room. And they wanted to get an espresso machine, and it was like something like 30,000 crowns. And I remember I objected because I thought it was a waste of taxpayers' money to buy a stupid 30,000 crowns, you know, Ferrari coffee machine for us mathematicians here. I regret that now. with the years, I've learned that. Well, I mean, yeah. Anyways, I should shut up. This is a math class and nothing else. So I wish you a good afternoon. Do the exercises for Friday, and yeah, that's it. See you on Friday. Do you have any question? All right. Bye-bye.
Thank you.